The only place we know that life exists is Earth. Our planet is in a Goldilocks zone. Not too hot, not too cold, just right. Closer to the sun, and we bake in the heat. Farther from the sun, we freeze to death, or we sink to the center of a surface-free gas giant like Jupiter or Saturn. Does that mean it's not possible for life to exist outside of the Goldilocks zone? We'll discuss this possibility next. Stay tuned. Is there a possibility of life in the outer solar system? It doesn't seem reasonable. The outer solar system is outside of the Goldilocks zone, the region where temperatures are just right for liquid water to exist on a planet. We know that we have a few basic requirements for life as we know it. The most obvious is liquid water. Some less obvious, but very important additional requirements include a planetary magnetic field that protects the planet from harmful blasts of solar radiation, an atmosphere to protect from harmful radiation like UV, X-rays, and gamma rays, a long-term stable land mass, but not too long-term because tectonics are vital in recycling life-sustaining materials, a long-term stable climate. Stability is required in the environment because it takes time for life to develop and adapt. Too much instability will limit life's ability to adapt. So as we consider the outer solar system, we'll first take a look at Jupiter's Galilean satellites. Their densities and appearance indicate that they're mostly made from rock and ice. They orbit in the equatorial plane of Jupiter. They are in circular orbits that orbit in the prograde direction. The innermost moon is Io. Io is roughly the size of our moon. It's in a very circular orbit in Jupiter's equatorial plane. It's also a very cold moon at only 120 Kelvin. That's minus 243 degrees Fahrenheit. In spite of the cold temperatures, Io has no surface ice. It has a very rocky crust. Io is among the most geologically active places in the solar system. Its surface is covered by volcanoes. Many have been viewed by spacecraft actively erupting, like this one. Here is a surface photo showing active volcanoes across most of its surface. What could be causing this type of activity? On Earth, it's plate tectonics, but Io is not large enough. The heat, as it turns out, is due to tidal stresses. Heat is being generated by continual stretching and compressing by interactions with Jupiter and Europa.
Io's orbit around Jupiter is pretty oblong, so sometimes it's closer, sometimes it's farther away. When it's closer, gravity is stronger, meaning the tidal forces make Io more football-shaped. As Io approaches the point on its orbit where it's closest to Jupiter, the tidal forces increase and its surface swells as much as 330 feet. Then it recedes again as it goes back around the other side. So, as Io orbits Jupiter, getting closer at some points than others, it's being stretched and compressed over and over, generating friction, which in turn generates heat. When tidal forces create heat, it's called tidal heating, and this strange phenomenon, a natural consequence of gravity, is what maintains Io's molten core and fuels its astonishing volcanic activity.
Surface maps like this one confirm what we'd expect. Few, if any, craters. All are being filled in by volcanic eruptions. Io's surface, therefore, is not stable long enough for life to adapt, so it is not a good candidate to search for life. Next, let's turn our attention to Europa, the next moon out from Jupiter. Europa is slightly smaller than our moon, and it is also in a fairly circular orbit. Europa's surface closely resembles a billiard ball. Its surface is covered with ice and fault lines covering its entire surface. It is also remarkably crater-free. The surface appears to be constantly changing. Ice blocks, like pieces of a puzzle, no longer appear to line up. Cracks in the surface are filled in with a darker material from below, likely liquid water. Life here wouldn't be on the surface, but it might be below it. Europa's fault lines appear to be filled in by liquid water from below its icy surface.
Imagine if you were trying to change the shape of an egg. What would happen to the shell? The shell would crack. And so when we look at the surface of Europa, we see lines all over the place, which are almost certainly marking the locations of cracks.
The cracks appear to open and close frequently. And the potential for these cracks to allow subsurface water to interact with the surface has important implications for the possibility of life on Europa.
Water from the ocean is going to rush up into the crack. When it rushes up, it's going to freeze, start to freeze. A few hours later, when the crack closes, it's going to squeeze that slush up to the surface. And so wherever we see these lines on Europa, there are double ridges, one ridge lining along each side of the crack.
Most of the water, no doubt, sloshes back down out of the crack to the ocean below.
Internal heat that melts the ice is generated by tidal forces between the Galilean satellites. All of them are in resonance. Each time they line up, they are internally squished and squeezed, generating heat, enough that keeps the liquid water from freezing. The icy crest would protect the subsurface ocean from harmful space radiation. Water ice has also been observed coming from plumes on Europa, confirming that water does exist subsurface. A final piece of evidence of a subsurface ocean is an induced magnetic field on Europa from Jupiter. Europa does not have the properties needed to produce its own magnetic field. The induced magnetic field requires a magnetic medium, in this case, salt water. The next moon out is Ganymede, the largest moon. Ganymede is similar to Europa in many ways. It too seems to be covered with a crust of ice. Its surface does have craters that expose a much brighter subsurface material, most likely water ice. Its surface too shows evidence of shifting and moving, again indicating a subsurface liquid water. There is obvious misalignment of features that were once aligned. These features would not be able to move on top of another solid surface. Ganymede also has a magnetic field that is most likely due to a saltwater layer below the icy crust. In fact, there may be several layers of ice on top of a rock layer. The rock layer may provide important minerals to any existing life forms. And finally, our outermost Galilean satellite, Callisto. Callisto has an ancient surface covered with craters. Its density also suggests it is a mostly rocky and icy world. Its craters, too, expose a bright layer of material, likely water ice, from below. Next, we'll turn to Saturn. There are two moons of interest. The small moon Enceladus has been thrust into the spotlight as the most likely place for life outside of the Earth. It's a tiny moon originally not thought to be of any interest. That changed with the Cassini mission. Cassini detected plumes of ejected water containing key life elements of carbon, hydrogen, nitrogen, and oxygen. Additional observations detected heat sources below the surface, a signature of the presence of liquid water. Though Enceladus doesn't have a magnetic field of its own, it does reside inside Saturn's magnetic field, meaning it would have protection from harmful space radiation. Saturn's largest moon, Titan, is also a place of interest. It is the only moon with its own atmosphere, a very thick one in fact, 60% thicker than Earth's. Why does such a small moon have its own atmosphere? Because Titan is exceedingly cold. At only 93 Kelvin, the low temperature more than compensates for the low surface gravity, allowing Titan to retain its atmosphere. It's so cold and such high pressure that methane exists in three phases: liquid, solid, and gas, just like water on Earth.
The mean temperature on its surface is almost 300 degrees below zero Fahrenheit. It is so cold, and water on the surface of Titan is frozen to such an extreme state, it behaves like rock. The rocks in this blurry photo taken by the Huygens lander are, in fact, water. It is so cold that hydrocarbons that are gases on Earth, such as methane and ethane, are in a liquid state on the surface of Titan. The Cassini flybys have spotted them.
We're seeing a lot of what looks like organic materials on the surface, and we're seeing large bodies of liquid, but it's not liquid water, it's liquid methane with possibly some ethane dissolved in it. There are huge lakes on the size of Great Lakes or small seas.
Before completely ruling out primitive life on these worlds due to the lack of sunlight, we need to remember that life exists at the bottom of the deepest Earth oceans, away from sunlight.
But as we explored the bottom of our own oceans, we found ecosystems that were completely independent from the sun. The organisms there relied on chemicals and energy released by hydrothermal vents. Bacteria there use chemosynthesis, not photosynthesis, to create energy for themselves. These bacteria coat the vent, where amphipods and copepods graze on them directly. Above them in the food chain are snails, shrimps, crabs, fish, eels, and a host more. Here the temperature is hot and the pressure is enormous, but if something similar to hydrothermal vents exists at the bottom of these moons' oceans, and that life isn't unique to only Earth, this is as good a place as any to look for life.
In spite of being well past the Goldilocks zone, we have found liquid water, protection from space and subsurface oceans and magnetic fields, and the stability we need for life to flourish. Hospitable environments do seem to exist outside of Earth. The life may not be intelligent, but we may only know with a visit from a spacecraft.
What's up?
What's up?
What's up? What's up? What's up? Oh man, we are not alone.